partial derivatives are just like derivatives, except that they're for multivariable functions where derivatives are for single variable functions. We all know how to take the derivative of a single variable function because there's just one variable in that function, so when we take the derivative with respect to that variable. We take the derivative of that variable. But how do we take the derivative when there are multiple variables inside the same function? So let's expand a little bit on this idea. What are partial derivatives used for? Well, let's go back to our understanding of a regular derivative for a single variable function. So if we have a function, let's say f of x is equal to x cubed. We could also write this as y equals x cubed, and it would mean the same thing. So we already know how to take the derivative of a function like this. If we want to find the derivative, we call the derivative f prime of x, and in this case, because of the kind of function that it is, we would simply use power rule to take the derivative, and the derivative of x cubed would be 3x squared. Now let's go back to the idea of a derivative. The derivative gives you the slope of a function at any particular point. So if I have the function x cubed, and I want to know its slope at a particular point, the slope being how fast the function is increasing or decreasing, or if it's staying flat, then I can take the derivative and I can evaluate the derivative at a particular point. So this derivative function, f prime of x, is 3x squared. This is a model for the rate of change of f of x anywhere. So if I wanted to say what is the slope or what is the rate of change at x equals 2 of the original function f of x, I would plug x equals 2 into the derivative, and I would say f prime of 2 is equal to 3 times 2 squared, which is 3 times 4, or 12. So what this tells me is that the original function f of x has a slope of positive 12, meaning that it's increasing because the slope is positive when x is equal to 2. If I plug a value into the derivative and the result is negative instead of positive, let's say I had gotten negative 12 instead of positive 12, that would tell me that the original function is decreasing. And we care about the slope because we care about whether the function is increasing or decreasing, or if it's flat, and if it's increasing or decreasing, how fast it's going up and down. So the derivative is important to us. So partial derivatives are the way that we find the derivative of a multivariable function. This was a single variable function. We only had x on the right-hand side. But if I instead had something like f of xy is equal to x squared y, I now have two different variables on the right-hand side. Instead of just x, I have both x and y in a multivariable function. So how am I going to take the derivative of this? I can't just take the derivative of the x and ignore the y, or take the derivative of the y and ignore the x. The x squared and the y, they're tied together. They affect each other. So I have to have a special way of taking the derivative of a function like this one. And that's what partial derivatives allow us to do. We can take the partial derivatives of this function, and together those partial derivatives are going to tell us the slope of the original function. That those partial derivatives will model the slope at any particular point. And then, just like we wanted to in this problem, look and see what the slope was at x equals 2, so we plugged 2 into the derivative function, we might want to find the slope of this function at the coordinate point 2, 3, and so we could find partial derivatives, we could plug in the point 2, 3, and those partial derivatives together would tell us the slope of the original function f of xy at the point 2, 3. So partial derivatives just allow us to take the derivative of a multivariable function, and they therefore, because they are the derivative of a multivariable function, they model how fast that multivariable function is increasing or decreasing, or if its slope is staying the same. So what exactly are partial derivatives? What does it mean when we say partial derivatives, and what do they look like? Well, you're always going to have the same number of partial derivatives that you have variables in your function. So in this example, again, we have two variables, x and y, which means that if we want to take partial derivatives of this function, we will have two partial derivatives. And it's going to be one for each variable, one partial derivative for x and one partial derivative for y. So let's go ahead and take a look at what those partial derivatives are going to be. So we'll have two partial derivatives, one with respect to x and the other with respect to y. And we'll talk again about what that means in a second. Let's start with the partial derivative with respect to x. First of all, there are two ways to express the partial derivative with respect to x, or two ways to write it. So the first one looks like this, f sub x, and you might see f sub x of x comma y. So with this xy in parentheses attached to it, you may see that. But the shorthand notation is f sub x with this little x. Or this notation here. And what this means, this symbol right here is called the partial symbol. You read this symbol as partial. So this is partial f divided by partial x, or the partial derivative of f with respect to x. So the letter on the top is always the function. So since this is the function f, we put f on the top. And the variable that you're taking the derivative with respect to goes on the bottom. So since we're going to be taking the derivative with respect to x goes on the bottom. So the partial derivative of f with respect to x. And here's how you get that. You look at your original function, and we're going to be taking the derivative with respect to x. What that means is that you're going to be differentiating the x variable like you would if this were a single variable function, because you're treating y and any other variables in the function, for that matter, as a constant. So this gets a little tricky, but in this function we have x squared times y. One trick I like to use is to think of the other variables as actual constants. So we say we're treating y as a constant, but what does that really mean? Well, let's actually think about replacing y with a constant, like for example, the number 3, or you could pick 2 or 7. It doesn't matter which constant, but you can think of it that way. So for example, if y were 3, then this function here would be x squared times 3, or 3x squared. So we'd have 3x squared. And let's keep in mind here that this 3 is representing our y. Okay, so if we had that, how would we take the derivative of that? Well, we would use power rule. We would bring the 2 down in front, and we get 3 times 2, and then we'd have x to the first power, because we'd get 2 minus 1 in the exponent is 1. So we get 3 times 2, x to the first, and this would end up being 6x. That's how we would find the derivative if we had 3x squared. Well, that's basically exactly what we have, because we're treating y like a constant. So it's just like this 3 sitting out here in front of the x squared, which means that all we have to do to find the derivative is follow this same pattern. Here, we brought the 2 down in front, so we would bring this 2 down in front, and we would get 2x. We'd still have x to the first power, because we would subtract 1 from the exponent and end up with 1. And the y would just stay there. So we'd end up with 2xy. Another way to think about that, other than this one here where you're treating y as a constant, is to, for every term, factor any of the other variables that you're treating as constants out in front. So if we rewrote this instead as y multiplied by x squared, this is helpful because you kind of pull the y outside and you can just focus on the x squared, what's inside the parentheses, because this is the only variable you care about. So then if you were to do it this way, you would say, okay, y is that constant? I'm just going to leave it there. The derivative of x squared is 2x. So I'd end up with y times 2x, or 2xy. So that's another way to look at it. Now let's practice again with the partial derivative with respect to y. So remember we said that we would have a partial derivative for each of the variables in our function. So we have an x and we have a y. We just took the partial derivative with respect to x. Now we need to take the partial derivative with respect to y. So as you might imagine, instead of f sub x, we can call it f sub y. And instead of the partial derivative of f with respect to x, we write that as the partial derivative of f with respect to y, or partial f, partial y. and this represents the partial derivative with respect to y. And now, of course, we do the opposite operation. In this case, we treat x as a constant, and we treat y as a variable. So if we use this method again, what we want to do is recognize that the entire x squared is a constant. So we kind of want to pull that out in front and rewrite this as x squared times y, because y is the only thing we care about. So x squared is that constant. It's just going to hang out in front there and stay. The derivative of y is 1. So our result then would be x squared times 1, which is just x squared. So we end up with x squared. Now these together, it's important to know, are our first order partial derivatives. You can think about them as first order partial derivatives because you only took the derivative one time. We took the derivative one time with respect to x. We took the derivative one time with respect to y. So because we took the derivative one time, these are first order partial derivatives. And we know that we have all of them because we had the x variable and the y variable, and we have a partial derivative with respect to x and a partial derivative with respect to y. And at this point, we want to talk about second order partial derivatives. So while this may seem a little intimidating, really we're just following the same process that we already took to get to this point with our first order partial derivatives. So we're treating now this 2xy, think about it as a brand new function. And we want to take the derivative with respect to both x and y because our original function had an x and a y, which means we need to take the derivative with respect to x and y, regardless of which variables still remain in this function. So if I take the partial derivative with respect to x of 2xy, I want to treat y as a constant again, because I'm differentiating with respect to x. So I could rewrite this, I could pull the y out in front and get y times 2x. So I let the y hang out there. It's like a constant coefficient. I don't have to worry about it. The derivative of 2x with respect to x is 2. So I'm going to get y times 2, or 2y. So the derivative with respect to x is 2y. But how do I write the second order partial derivative with respect to x? Well, just like before, there were two ways to express this in terms of notation. Again, there are two ways to express second order partial derivatives. So the second order partial derivative with respect to x, unsurprisingly, instead of just f sub x, it would be f sub xx. So the second order partial derivative with respect to x, which makes sense because we're taking the partial derivative with respect to x 2 times. We took it with respect to x here, and then again with respect to x of our result. So we took the partial derivative with respect to x twice, so we write f sub xx. Or we could also write this in this notation here. And here's what that looks like. It'll be partial squared f partial x squared. You always have partial squared f in the numerator, and then partial x squared when we take the derivative with respect to x 2 times in a row. And both of these notation mean the same thing. Now what about this second order partial derivative here with respect to y? Well, we first took the derivative with respect to x. Now we're taking the derivative of the result with respect to y. So first, let's just differentiate this with respect to y. What we want to do is pull out everything else other than the y out in front. So we can pull out the 2x and we can write this as 2x and then y in parentheses. Well, the derivative of y is 1, so we get 2x times 1, or just 2x. So the derivative here will be 2x. Now, how do we indicate this in terms of notation? Well, again, we have both sets of notation, but this one gets a little tricky. So for this subscription notation here, where we have subscripts, we write that as f sub xy. But for this other kind of notation, we still have partial squared f in our numerator, but in our denominator, we have partial y, partial x. And there's something important worth noting here about how to read partial derivative notation. So when you use this subscription notation and you have the subscripts here, you always indicate which partial derivative you took first, left to right. So in other words, to get here to 2x, we first took the partial derivative with respect to x and then y, which is why we write f sub xy. We did x first, then y. It's left to right. But in this notation here on the bottom, it's exactly the opposite. You indicate which partial derivative you took first on the right-hand side, and you read from right to left. So because this is x on the right and y on the left, and we read from right to left, this says we took the derivative first with respect to x and then y. So they're backwards, and depending on which notation you use, you want to make sure that you get these in the right order. So we'll look at a second example of that when we do the second order partial derivatives here. If we take the second order partial derivative with respect to y again, we already took the first order partial derivative with respect to y. Now we want to do y again. That is, of course, f sub yy, or partial squared f over partial y squared. And that's going to be equal to, here the first order partial derivative with respect to y was x squared. So our result was x squared. We need to take the derivative of this with respect to y. And you might be wondering at this point, how are we going to do that when we have no y involved? Well, remember, we're treating x like a constant. So let's pretend again that x is a constant like 3. So I would get 3 squared, or 9. So the partial derivative here would be 9, and now I'm saying, okay, what's the partial derivative of 9 with respect to y? Well, remember from single variable functions, the derivative of a constant is always 0. So the derivative of that will be 0. And another way to remember that is if you're taking the partial derivative of something and the variable that you're differentiating does not show up in the function, then the whole function is a constant and the derivative will of course be 0. So because we're differentiating this with respect to y, and there's no y there's no y present, then the derivative will be 0. So we can say here that the derivative is 0. And then finally, this is the last second order partial derivative. This one we're saying is the partial derivative with respect to y and then x. So if we were going to write that in subscription notation, we would say with respect to y and then x. And if we were going to write it in this notation, we would say partial squared f over partial, we said with respect to y first, so that goes on the right side, then with respect to x. So notice how these are exactly opposite of this notation here. So here, with respect to y, and now with respect to x, we're taking the partial derivative of x squared with respect to x. And that's no different than a single variable function. We want to differentiate x. All we have left is x. That's easy. The derivative of x squared, 2x. No problem. And now this whole row here, all 4 of these derivatives, we call our second order partial derivatives. Now let's talk about a couple really important things here. First of all, second order partial derivatives. In a function with 2 variables, we're always going to have 4 of them, because if there's 2 variables in the original function, you have 2 first order partial derivatives, and then you're going to double that and you're going to have 4 second order partial derivatives. If we, for example, took third order partial derivatives, we would double that again, and there would be 8 third order partial derivatives, 2 for each of these 4. So that's one thing to know. Another thing to know is that these 2 derivatives here in the middle, let's indicate our results here. So these 2 things, these values are always going to be equal to one another. These 2 are called the mixed second order partial derivatives or the cross second order partial derivatives because you're differentiating with respect to each variable. When we took this path, we went first x, then y. When we took this path, we went first y, then x. But either way, we differentiated with respect to both variables, which is why they're called the mixed second-order partial derivatives. And you will always end up with the same value, and as long as the original function is continuous everywhere in its domain, and all the partial derivatives are also defined and continuous, then these mixed second-order partial derivatives will always have the same value, which means that you don't actually need to find both of them unless you're explicitly asked to do so. You can just find one of them, either x then y, or y then x, because you know that you're going to end up with the same value. So that's what we mean when we say the mixed partial derivatives. So why is it the case that the mixed partial derivatives are always equal to one another? Well, it's a little difficult to explain and certainly difficult to understand, but we're going to try just to get a little bit of a visualization here. So let's say that we have this function, and I don't even know the equation of this function. It's just a plane, and it's defined by these edges here, but it intersects the x-axis at this point here, intersects the y-axis here, and intersects the z-axis. So it's a plane, and it's kind of tilted back up top here, and then as we go down here, it comes forward toward us or closer to us. And so then I've drawn in that it creates a little shadow in the first quadrant of the xy plane right here underneath it. So when we talk about partial derivatives of a function, so we have the partial derivative with respect to f of x and the partial derivative with respect to f of y. These are the first order partial derivatives of a function. Well, what these mean, the first order partial derivative with respect to x means slope in the x direction, or the slope in the direction of x, the slope toward x. And then, of course, the partial derivative with respect to y means slope in the y direction. So let's pretend then that I'm interested in the derivative of this surface at this point right here. Let's say this is a point on the surface. So the surface is kind of reclining away from us, and that point is just sitting right on this surface. If I find the partial derivative with respect to x at that exact point, what I'm saying is the slope of this function, this surface, in the derivative of x. Well, you can see x is this direction, so if I kind of draw a parallel line, I'm saying the slope in this direction here. If I take the partial derivative with respect to y, I'm looking for slope in the y direction, so this is my y direction right here. So toward x, the function might be changing at a certain rate. Toward y, it might be changing at a different rate. Even looking at this sort of reclined plane, if I'm moving toward x or I'm moving toward y out in the positive direction of either one of those, then the slope is going to be negative. The function is decreasing because as I move out in the positive direction of x or the positive direction of y, the plane, the surface, is moving down toward the negative direction of z. So both my partial derivatives should be negative. So I have slope in the x direction, slope in the y direction. The reason that the mixed second-order partial derivatives are the same is kind of just because the derivative, remember, is an infinitely small increment. If I just look at an infinitely small change in the x direction and an infinitely small change in the y direction, the smaller the change I make until I get to a point where it's infinitely small is going to give me just the general change at this point that I'm interested in, the slope of the function overall, as opposed to the slope in the x direction or the slope in the y direction. Because if I'm taking an infinitely small increment, I'm not really moving away from this point out a distance toward x or out a distance toward y. I'm just right at that point trying to get a feel for the slope right there. So when I take the mixed second order partial derivatives, I'm taking into account both the change in the x direction and the change in the y direction and sort of putting those together to get the change in general at that exact point. So hopefully that gives you an idea of why the mixed partial derivatives are always equal to one another. Now before we wrap up, let's do one slightly more complicated example. Let's say we have f of xy is equal to e to the xy. So the first thing we want to do is find first order partial derivatives. So if we go ahead and say we're going to have one derivative here and one derivative here, first we want to find the partial derivative with respect to x. So we can go ahead and call that the partial derivative of f with respect to x is going to be equal to, now here we have to take into account the fact that we have the exponential function. Remember that the derivative, when we say the derivative of e to the x, that's always just e to the x, the function itself, right? We differentiate e to the x and the result is still e to the x. Well, similarly here, if I'm going to differentiate e to the xy, the result is still going to be e to the xy, because we know from single variable calculus that nothing changes. So my derivative here is still e to the xy. However, just like with single variable calculus, you always have to remember in partial derivative problems to apply chain rule. And in the case of the exponential function here, e to the xy, when we take the derivative, we get e to the xy, but then we apply chain rule, which means we multiply by the derivative of the inside function. The inside function is xy, and the derivative of xy is affected by our partial derivative. We're taking the partial derivative with respect to x. So what now is the derivative of xy with respect to x? Well, if we look at that, xy, and we're interested in x, we can factor out the y in front, and we can write that as yx. Now the derivative with respect to x, y acts like a constant coefficient. It stays out in front. The derivative of x is 1, so we get y times 1, or just y. Which means when we apply chain rule, we have to multiply this here by y, and we end up with y times e to the xy. Now if we move over here to the partial derivative with respect to y, we'll see the same thing play out. So the partial derivative of f with respect to y is going to be equal to the derivative of e to the xy, just like single variable calculus. When we differentiate that, nothing changes. So we get e to the xy. But then we have to apply chain rule, which means we have to multiply by the derivative of the inside function. The inside function is xy, and so we need to multiply by the derivative of xy. So the derivative of xy with respect to y, since that's what we're differentiating, if we look at that, we pull the x out in front, and we can call it x times y, taking the derivative of that with respect to y. Well, the x acts like a constant coefficient out in front, and the derivative of y is 1. So we get x times 1, or just x, which means we have to multiply this by x, and we get x times e to the xy. Now if we look at second order partial derivatives, we'll first take the derivative of this with respect to x again. So that'll be partial squared f partial x squared, the second order partial derivative with respect to x. So we have y e to the xy. Your derivative rules from single variable calculus all still apply. So because we're taking the second order partial derivative with respect to x, remember that we're treating y as a constant. So this y out in front here is just like a constant coefficient. It's like having 3e to the xy. And that 3 can just hang out there in front and not affect anything. We can just leave it right where it is. So we can almost even ignore that. And then again, we're just taking the derivative of e to the xy with respect to x. And we already know what that is. We already took the derivative of e to the xy with respect to x, and the result was y e to the xy. So the derivative of this with respect to x will be y e to the xy. But we have this other y still. So the final result will be y squared e to the xy. And then the partial derivative with respect to x, and then here we took the partial derivative of x first and then y, is going to be equal to, so now we're differentiating this with respect to y. And because we're doing that, we now have to apply product rule from single variable calculus because we have the product of two functions. We have two functions that are in terms of y. The first one is y. The second one is e to the xy. So we need to apply product rule to take the derivative. We didn't have to do that here with x because with x, y was a constant. So this y in front here could just be a constant coefficient in front. We didn't have to treat it like a variable. But now we do because we're differentiating with respect to y. So remember, product rule tells us that we want to take the derivative of one function first. So we'll take the derivative of y, and the derivative of y with respect to y is, of course, 1. Then we multiply that by the other function without doing anything to it. So we multiply that by e to the xy. Then we add to that the opposite situation. This time we leave y alone and we do nothing to that, but we multiply by the derivative of the other function. So the derivative of e to the xy with respect to y, well, we actually already found that. Up here we had e to the xy, and we took the derivative with respect to y. The result was xe to the xy. So we can multiply this by xe to the xy. And when we simplify this here, we end up with e to the xy plus xy e to the xy. We could leave our answer this way, or if we wanted to, we could factor out an e to the xy, and we would get e to the xy times 1 plus xy. Now I'll let you verify if you want to that this is the same result you get when you differentiate this first order partial derivative with respect to x, because here we did the partial derivative with respect to y, and then if we took the partial derivative with respect to x, that would be a mixed derivative equal to this mixed derivative here. So we'll get this either way. So all we have left then is the second order partial derivative with respect to y. So that'll be the second order partial derivative with respect to y, which means we're differentiating xe to the xy with respect to y. And again, just like over here, in this case, we hold x as a constant. So this x out in front here gets treated like a constant. It can just be a constant coefficient. We don't have to use product rule or anything like that because we're not treating x like a variable. So then we're just taking the derivative of e to the xy with respect to y, which again, we already did here. We had e to the xy, we took the derivative with respect to y. So the derivative of this portion we know is xe to the xy, but we still have this x hanging out in front, so we have to include it too, and we can say that the second derivative is then x squared, e to the xy. The only other thing to mention here, now that we've found all of the first order and second order partial derivatives, is that at this point, you have functions that model all the first derivatives, all the second derivatives. But a lot of times you're going to need to find a partial derivative at a particular point. So for example, we're going to want the partial derivative with respect to x at the point 2, 3, like we talked about earlier in the video. Or you're going to want to find the second order partial derivative with respect to y at the point 2, 3. Well, we have all these functions that model these derivatives. If we ever want to find the value of one of these at a particular point, all we do is we plug in the coordinate point that we're interested in into that partial derivative. So for example, if we want to find the value of the second derivative with respect to x, then we're looking at the second derivative here with respect to x. Let's say we want to find that at the point 2, 3. All we do is we take the same notation here, and then we add in here that we're evaluating this at the point 2, 3. So that's just like saying evaluate the second order partial derivative with respect to x at the point 2, 3. And then we just plug that point in here. So y is 3, x is 2. So 3 squared is going to give us 9. And then e to the 2 times 3 is 6, so we get 9e to the 6th. So while you can find these partial derivatives, all these functions that model the first and second order partial derivatives, if you need to evaluate at a particular point, all you do is take that point, plug it into the function you found, and that will tell you the value of that partial derivative at that particular point. I hope that video helped you, and if it did, hit that like button, make sure to subscribe, and I'll see you in the next video.